This particular presentation is about the second module of the subject CS463 Digital Image Processing. The subject is offered as an elective to the 7th semester Computer Science and Engineering students under KTU. Myself, Harikrishnan M., Assistant Professor, Department of Computer Science and Engineering at Rajagiri School of Engineering and Technology. This is the syllabus for the second module as prescribed by the university. Image transforms and its properties, and namely that of unitary transforms, discrete Fourier transforms, discrete cosine transform, Walsh transform, and Hadamard transform. In this particular presentation, I will be discussing about image transforms and the properties of unitary transforms and DFT. For DCT, Walsh, and Hadamards, I will be preparing a separate video presentation. Now, what do you mean by image transforms? Image transforms usually refer to a class of unitary matrices that are used for representing images. This necessity arises where representing images for performing various image processing operations. Now, just as a one-dimensional function is represented using a basis function, images can be represented using basis images. These basis images are generated using unitary matrices. Suppose you have an n by n image. Alternatively, using image transformation, this image can be represented or viewed as an n square by 1 vector. What an image transform basically does is it provides a set of coordinates or basis vectors for the vector space. Now, these are examples of various image transforms. Image transforms are mainly classified into separable transforms and statistical transforms. An example for a statistical transform is Hotelling transformation. For separable transforms, there are various examples: DFT, DCT, Hadamard, Walsh, Slant, Haar, to name a few. Now, what do you mean by unitary transform? A unitary transform is represented as V is equal to AU, where U is a one-dimensional sequence where the value of n varies from 0 to n minus 1. So, this particular one-dimensional sequence is represented as a vector U of size n, and the unitary transformation is written as capital V is equal to A into U, which implies that V of k is summation over n from 0 to n minus 1, A of k comma n into U of n, where the value of k varies from 0 to n minus 1. So, here the inverse of A is the same as A raised to star t. So, therefore, you can represent U as A raised to star t into V. So, therefore, U of n can be recreated using this particular equation given here. Now, the columns of the matrix A raised to star t are known as basis vectors of A. The series coefficients V of k given here represents a original sequence U of n, and these are completely useful in areas such as filtering, data compression, feature extraction, and other analysis of images. Now, these are examples of basis vectors of 8 by 8 orthogonal transforms. Given here are the basis vectors of transforms such as cosine transform, sine transform, Hadamard transform, Haar transform, Slant transform, and the Kernel-Liouville transform for various values of k and n. In the context of image processing, a general orthogonal series expansion for an n by n image represented as U of mn is basically a pair of transformations that are of the form V of kl and U of mn. So, here V of kl is the transform matrix and U of mn is the recreated one. So, you use U of mn and A kl of mn to create the matrix V of kl, and V of kl and A star kl of mn are used to recreate U of mn. Here A kl of mn are known as image transforms, and they are a set of complete orthonormal discrete basis functions that satisfy the properties of orthonormality and completeness. The elements V of kl indicated here are called transform coefficients, and capital V is called the transformed image. The transformed image V is calculated as A into U. Dimensionality of image transforms are studied in terms of their Kronecker product separability. Now, what do you mean by a Kronecker product? It will be discussed in an upcoming slide. An arbitrary one-dimensional transformation represented as y is equal to ax is called separable if A can be represented as a Kronecker product of smaller matrices. So, if y equal to ax can be reduced to the separable 2D transformation y equal to a1 x a2 transpose, where x and y are matrices that map into the vectors small x and small y respectively by row ordering, then you can say that the arbitrary transformation y equal to x is separable. Image transforms such as discrete Fourier transform, sine transform, cosine transform, Hadamard, Haar, and Slant can be factored as Kronecker products of several smaller size matrices. So therefore, all these transformations are fast transformations because they lead to fast algorithms for their implementation. So therefore, such transforms are known as fast image transforms. Now this is how the Kronecker product of two matrices are calculated. Suppose you have a matrix A which is an M by N matrix and you have a matrix B which is a P by Q matrix. Then the Kronecker product denoted as A cross B is a PM by Qn block matrix. This is obtained by multiplying every element of A with all the elements of B. An example is shown in the next slide. Suppose you are finding the Kronecker product of two matrices. Matrix A is denoted here as 1, 2, 3, 4 and matrix B is denoted as 0, 5, 6, 7. So the Kronecker product is obtained by multiplying 1 with 0, 5, 6, 7, 2 with 0, 5, 6, 7, 3 with 0, 5, 6, 7 and 4 with 0, 5, 6, 7. Here A and B are both 2 by 2 matrices. So therefore the Kronecker product matrix will be a block matrix with dimension 4 by 4. Another example is given below where two matrices are multiplied to get the Kronecker product. One is a 2 by 3 matrix and the other is a 4 by 4 matrix. So the resultant will be an 8 by 12 matrix. Now what are the different properties of unitary transforms? The first property is about energy conservation and rotation. Unitary transforms preserve the signal energy or equivalently the length of the vector u in the n-dimensional vector space. All unitary transformations are simply a rotation of the vector u in the n-dimensional vector space. For two-dimensional unitary transformations, it can be proven that double summation over m and n from 0 to n minus 1 of u of mn the whole square is the same as double summation over k and l from 0 to n minus 1 of v of kl the whole square. Here u of mn is the original sequence and v of kl is the unitary transformed vector. Another property of unitary transform is about energy compaction and variances of transform coefficients. Most unitary transformations have a tendency to pack a large fraction of the average energy of the image into a relatively few components of the transform coefficients. Since the total energy is preserved, this means that many of the transform coefficients will contain very little energy. The average energy of the transform coefficients represented as V of k tends to be unevenly distributed, although it may be evenly distributed for the input sequence u of n. Another property is based on decorrelation. Suppose the input vector elements are highly correlated, the unitary transformation coefficients tend to be uncorrelated. There are other properties as well for unitary transforms, some of them which are the determinant and the eigenvalues of a unitary matrix will have unit magnitude, entropy of a random vector is preserved under unitary transformation, and finally, since entropy is a measure of average information, this means that information is preserved under unitary transformation as well. Now the next transform that you have to learn is discrete Fourier transform, which is represented as DFT. The DFT of a sequence u of n where n varies from 0 to n minus 1 is defined as V of k is summation over n from 0 to n minus 1 of u of n into wn kn, where the value k varies from 0 to n minus 1 and wn is calculated as exponent of minus j2 pi by n. Here the inverse transform is calculated using the given equation where you will get u of n, where the value of n varies from 0 to n minus 1. In image processing, it is more convenient to consider unitary DFT, which is defined as V of k is 1 by root n into summation over n from n minus 1 into u of n into w kn n. This is obtained from a normal DFT by multiplying the normal transform matrix with 1 by root n. The same is the case for inverse transformation. Now this is an example about how DFT acts as a mathematic prism. DFT basically divides a signal into all its constituent signals. This is an example with reference to image processing. You have an original image of a cameraman and its corresponding DFT representation. Now if the image is blurred, you can see that the DFT representation also varies. These are examples of two-dimensional DFT representation of various images and the spectra. This is how inverse DFT is applied to recreate the original image. Now what are the properties of DFT or unitary DFT? Discrete Fourier transform as well as unitary DFT matrices are both symmetric. That is, F inverse is the same as F star. DFT is the sample spectrum of the finite sequence U of n extended by zeros outside the interval of 0 to n minus 1. DFT and unitary DFT of dimension n can be implemented by a fast algorithm in big O of n log n to the base 2 operations. Therefore, such Fourier transforms are also known as fast Fourier transforms or FFT. Other properties are DFT and unitary DFT of a real sequence x of n where n varies from 0 to n minus 1 is conjugate symmetric about n by 2. The basis vectors of the unitary DFT are the orthonormal eigenvectors of any circular matrix, or the eigenvalues of a circular matrix are given by the DFT of its first column. A linear convolution of two sequences can also be obtained by a fast Fourier transform by embedding it into a circular convolution. These are the two main references used to prepare these slides. One is the textbook on fundamentals of digital image processing by Anil K. Jain, and the other is a link which is a PDF file which was used to obtain the images as well as some of the content of this particular presentation. Thank you all for your patient listening. I will meet you with the next presentation on the remaining part of the second module.